So hey everyone. So as the title would suggest, I'm going to be talking about looking at a nanoparticle suspension in water and looking at how the glass transition temperature of the nanoparticles affects the final morphology of the final dried microparticle. So first off, just to look at why does dried particle morphology matter? Well, it's used in spray dryers. So spray drying is a process that starts off with a feed solution and is nebulized and heated. So you end up with final dried particles. And it's used in many industries like milk formulation, cosmetics, pharmaceuticals. And the final morphology of the dried particle has quite an effect on the chemical and physical properties of those particles. So just to give you an example, in pharmaceuticals, if you were looking to formulate an inhaled drug, you would want that to have the particles to have a high surface area and a low density. So being able to understand what forms those types of morphologies just makes it easier to be able to create formulations that will have the morphology that you want. Also, respiratory aerosol are an example of aerosol droplets that have inclusions in them. So again, understanding how these droplets dry and understanding the morphology as they form just help us understand the processes a little bit better about how respiratory aerosol droplets dry in the air. Surface enrichment of the droplets is something that can kind of steer the morphology one direction or another. So the surface enrichment happens as you have the aerosol droplets that have so the water droplets that have the inclusions in, and as those droplets evaporate, the surface recedes and the nanoparticles can get caught on the outside of the surface and cause surface enrichment. We can kind of quantify this using a dimensionless number called the Peclet number, and that's essentially just the ratio of the evaporation rate to the diffusion constant of the nanoparticles. And if the Peclet number is very high, the evaporation rate is very quick, so you get this enrichment happening early on in the process because the nanoparticles can't diffuse throughout the bulk fast enough to kind of move away from the receding surface. And that'll give you the kind of top scenario, and then so scenario E, and then on the bottom, that's got a low Peclet number where the nanoparticles can diffuse into the droplet bulk, and kind of the surface enrichment happens later on in the process, and you get these kind of small dense particles. So the scenario E that I mentioned, where it forms the shell earlier on in the process, it forms a kind of bigger shell radially that's a lot thinner. And as the water continues to evaporate from within it, you get this compressive force on the shell, which eventually causes it to buckle. And you get these kind of cooled buckled morphologies as seen at the top, versus on the bottom, where you have the thicker, kind of smaller particles that are more resistant to the buckling. That happens because they tend to form stronger shells. So you end up with these dense spherical particles. There has been some work already looking at the glass transition temperature and the effect of the nanoparticles on the final morphology of the particle. So just to quickly mention, the glass transition temperature is the point at which usually a polymer goes from a kind of hard, brittle material below it to above it being more soft, malleable kind of material that has some level of kind of viscous flow to it. And this study here looked at two microparticles within a droplet, which were polystyrene and silica, and they found that as you increase the volume fraction of the silica nanoparticles, of the polystyrene nanoparticles, which have the lower TG, you find that there was slightly more buckling, as you can see in kind of the bottom right hand corner of this plot. But there were quite a few limitations with this study. So they looked at sessile droplets that were microliter sized, so millimeter in diameter, and they were drying on a surface, which isn't particularly relevant to that seen in spray dryers. And also they were looking at two materials that have TGs of above room temperature. So none of these, so the polystyrene and the silica won't yet have kind of moved from the hard brittle material into the softer, more malleable. So they're kind of comparing hard and then even harder nanoparticles here, rather than the softer regime. So to provide more of a kind of comprehensive study of this, my study looked at 4 different nanoparticles which were made at the University of Sheffield, and they had 4 different TGs. They were monodisperse, and they had 4 different TGs ranging from below room temperature to above. So we can kind of see the full scheme of, the really soft ones versus the hard brittle ones. And I also did a study. The study was using 3 picolitre size droplets, which are much more relevant to the types of things seen in spray dryers. So methodology-wise, I've kind of used 2 main instruments for this. The first of which being the comparative kinetics electrodynamic balance, where you essentially inject a single droplet into a chamber using droplet on-demand dispensers. It's held in the null point of electrodynamic field using, so an AC voltage is applied, which stabilizes it kind of horizontally, and then a DC voltage is applied, which stabilizes it vertically, and counteracts the effect of gravity. You can then shine a laser in, which collect the scattered light from the droplet and use those that elastically scattered light and the fringes that you get from that to infer the droplet radius. And then also you can control the RH using wet and dry nitrogen flow, and the temperature can be controlled with ethylene glycol coolant. So we can change the conditions that we do these experiments in. I should also mention we have 2 droplet on-demand dispensers, one of which dispenses the sample, which would be, in this case, the nanoparticle suspension, and the other dispenses pure water. So we have a kind of experimental something to kind of compare it to, and it helps us also, we can then model the RH using the water probe. Also use the falling droplet column paired with scanning electron microscopy. So in this, you use the same droplet on-demand dispensers, dispensed at the top of a long column, and they dry under the same conditions as we used in the EDB, so the same RH and temperature. And then at the bottom, once they're dried, we collect them on a glass slide, which we can then take and use to do SEM analysis and get these pictures from, so we can kind of study the morphology visually. So to jump straight into the results, these are the EDB measurements of the 4 different samples, as you can see, and each of the 4 different samples was done at 4 different RHs to look at the effect of the RH on the evaporation kinetics as well. What we found was that, well, I should also mention, so these are the evaporation curves, radius versus time plots, and the black line, which is somewhat difficult to see in some of them, but the black line is a modelled evaporation curve of pure water using the SADCAP model that was developed in the group. And you can see that the SADCAP black line follows each of the curves really nicely. So they all kind of overlap really nicely, and you can see from that we can't really see that the nanoparticles have changed the evaporation kinetics of the particles, given that they're acting as if they would if they were pure water. So at these concentrations, we can kind of determine that the evaporation kinetics aren't changed by the nanoparticles, but they are, of course, changed by the relative humidity. So as you increase the relative humidity, you're slowing the evaporation rate. And then just to kind of corroborate this, we this is the same curves from the last slide, but normalized using the initial radius. And then this is compared with the experimental water evaporation curves that I mentioned earlier with the probe measurement. And again, you can see these line up really nicely, so we don't see any change in the evaporation kinetics based on the nanoparticle suspension. So no effect of the evaporation kinetics. Then jumping into the SEM images, these are this kind of tableau of the different RHs, and again the different glass transition temperatures moving down the rows. And just straight off the bat, you can see that for most of the samples, as you move from left to right, so as you move up the RH and you decrease the Peclet number, most of the samples go from buckled, or at least donut shaped, to spherical, as is expected and has been shown in previous literature. But the kind of main outlier that you can see in that is the top row, which is the minus 30.4 TG, in which you can see that all of the microparticles have buckled. So to explore that a little bit more, this is just a comparison of the 45% RHs and the lowest and highest TGs. These are just 2 pictures from each sample. And you can see that, there's the high TG is spherical and the low is buckled. So what we think is going on here is that the nanoparticles formed from the low TG samples are softer because they've kind of undergone that transition from the hard, brittle particles to the soft ones. So when they merge to form the initial shell as they dry, even though it's quite a small shell that has quite a thick radius, actually the shell itself is quite soft. So it's mechanically softer than the high TG shells, so it's less resistant to the buckling, and therefore you get this buckling even at the high RHs, which has not before been seen. To kind of apply a more of a numerical value to this, I did some circularity calculations. For me, I did this by using the surface area of the particle divided by the surface area of the maximum enclosing circle once the image had been binarized. So this is excluding the surface area of the particle, excludes any voids. And yeah, I ended up with this plot on the right, which is the glass transition temperature versus the relative humidity. And you can see that as at the low glass transition temperature and low relative humidity, so the fastest evaporation rate, you get the lowest circularity, which is what you would expect. Moving to the high relative humidity and high glass transition temperature, where you get the high circularity. And then there's this kind of transition regime in the middle, where if you have a high glass transition temperature, you kind of, is that in-between section as well as a high relative humidity. So this just kind of matches quite nicely the SEM images that I showed you in the last slide. Okay, so to conclude, we found that the glass transition temperature of the nanoparticles doesn't affect the evaporation kinetics of the aerosol droplets when compared to pure water at the concentration of 2% that we used. But we did find that it does affect the buckling of the shells. So for the 2 microparticles that have the same Peclet number, if it has a low TG and is therefore a softer shell, it buckles a lot more easily compared to the microparticles that are made up of the nanoparticles that have the high TG, which don't buckle as easily because they have a high mechanical strength. In the future, I'm still waiting on some AFM measurements to look at the surface topography and then also measure the Young's moduli of the dried microparticles, which will really help us to determine the kind of mechanical strength is what's at play here. Yeah, I'd like to acknowledge the Bristol Aerosol Research Centre, Bristol, Sheffield, and the EPSRC CDT.
Thank you very much. So do we have any questions for Sorrel? Over there, Cam, thank you.
Thank you. Very nice. Question: the zeta potential of your plot. Could you check that? Could that can affect the buckling behavior?
No, I have not.
I think it's worth checking. If the zeta potential is which way around is it too little, you don't get any buckling.
Okay.
So have a look.
Yeah.
Very nice.
Okay.
Cam, just behind.
Hiya. With your softer nanoparticles, do you think that they would film form on the surface rather than stay a discrete nanoparticle?
So that was kind of what we were testing with the evaporation kinetics. So we thought that if they did merge completely and form kind of film, that would in some way hinder the evaporation of the water from within them. So we assumed that we'd see some kind of deviation from pure water in the evaporation kinetic curves. But as you saw, we didn't see any kind of deviation, or we saw no slowing of the evaporation kinetics. So we assumed that they are still staying somewhat as discrete nanoparticles. But equally, that's something that AFM will hopefully elucidate a little bit further. And we also think that possibly it's not the time frame that is happening is so slow that it's actually not kind of like compressing fast enough to cause that full compression of a film.
Yeah. And also as well, because you're doing work with single droplets, how well do you think actually spray drying those another product? Do you think you get a good product out of it?
Yeah, so this is actually someone in the group kind of doing work connecting the points between the single droplet and the spray drying. There is that kind of, because the conditions in the spray dryer are different to what we're using, so it's high temperature and stuff. But if you can kind of find a way to model the Peclet numbers in the same way, I think they are quite comparable. And hopefully we would see the same kind of results as in spray dryer.
Great.
Okay, one more.
From out did you look at the what some people call the jamming point and how that changes with your Peclet number?
No, what's the jamming?
The jamming point is where your essentially your curve finishes, well, probably where it finishes, where the size doesn't change anymore.
Oh yes, like the locking.
Locking.
Yeah, that's right. Yeah, so the kind of, as you can see, go back to the curves. So here, where you see that the curves suddenly go really messy, That's where we consider the locking point to be, because that's kind of when the sizing of the EDB, they can't size it quite as well, either because the morphology is no longer homogeneous, or the refractive index has kind of changed. So yeah, we've considered that the locking point of the droplets. And if you do kind of comparisons between that size there and the SEM images, they are fairly comparable, accounting for the fact that the droplets formed in the SEM images usually have a lower starting diameter. Yeah, I don't think they kind of degrade or shrink much further after that locking point that we see in the EDB.
I think they change with drying rate.
Oh, it's a change of drying rate. Yeah, so they do, I think, I have looked at this, and I think they do lock at a higher radius if they're drying kind of much faster, because they don't have time to kind of assemble in the same way. But yeah, I have looked at that. I haven't got the results in.
Okay. Great, thank you very much.